So this is the first in a series of tutorial videos, just reviewing some things we've already done. So the first one we're going to look at is the constant velocity particle model, which applies for particles, objects that are in constant velocity motion. So in other words, their velocity is not changing. So first thing we're going to do is let's take a look at the Tumble Buggy lab. So remember in this lab we had the little tumble buggy that moved at basically what appeared to be a constant speed, and as the buggy moved along the floor, we marked the floor, put pieces of tape, marker, whatever, at its position at a given time interval. That could be every second, every 2 seconds, every 3 seconds. The example I have here, just to make things simple, I did this for every second. So what we see on our motion map are just the little dots, and so this is the first dot. So sometimes we'll go ahead and label this the starting point, and then this is the last dot that we marked, so we're just going to label that last. Okay, and then what we're going to do is plot this on the graph. So for our data here, we could go ahead and write out a data table, which is what you did for the Tumble Buggy lab, but we can go straight from the motion map to a graph. Now, the key thing that most people forget is that the first dot here is when time equals 0, not time equals 1. So that's where the buggy was when we started the stopwatch. That was its starting position along our number line. Okay, notice here I did not start at 0, just so we could see what would happen if we're starting somewhere else. For a lot of our algebraic problems, we will often be starting at 0, or you can just call where we're starting 0. And you guys will see that in the future. Maybe you already have seen it. So this is at time 0. And since these are all at intervals of 1 second, this is at time equals 1, this guy is at time equals 2, and this guy is at time equals 3. And so we could go ahead and label those, or again, putting it in a data table, you just start your data table at t equals 0, and then put in the locations for each of these dots. So now I'm going to plot these on our graph over here. So at t equals 0, we're starting at 1 meter. Okay, so this is our starting place right here. So we started the stopwatch at 1 meter. 1 second later, the buggy was located at 3 meters. So I start down here at 1, follow that up to the 3 meter mark. Then next I have at t equals 2, we're at 5 meters. So I go all the way up here to 5 meters. And then for t equals 3, we're at 7 meters. So I find 3 here. I follow that all the way up till 7. And then I go ahead and mark there. So there's our dots. Hopefully we see that this looks like a pretty linear line. Now I have so-called perfect data here. As you know, in real life, data is not necessarily perfect. It's kind of messy. We have some experimental error involved. So usually your data points will not look this neat and clean, but for this example, I made them neat and clean. Then you'd want to take a ruler and then draw a best fit line. Now I have a hard time putting a ruler up to my computer, so I'm just gonna do my best freehand best fit line. However, you always want to use a ruler to make sure you're getting that perfectly still. Okay, so there's my line, and of course we always want to have a title on our graphs. I kind of missed that, so we'll just say position versus time. You can also call it Tumble Buggy lab summary, that's fine too. So our next step is going to be to write out our equation of the line. So we see this is pretty linear, and you guys know from math class that this is the equation for a linear line. So the generic format is y equals mx plus b. So let's just do a quick review of what all those letters mean. So the first one, y, that's the variable plotted on the vertical axis or the y-axis. In this case, that happens to be position. And what makes our lives even more confusing in physics when we're talking about horizontal position versus vertical position, we often use the letter x. Okay, so x is position horizontally. So if we're moving across a floor, we're going to use x for position and stick that instead of y. Sorry, that's confusing. If that is too confusing for you, you can use d for distance. That's okay. Technically, this is position as opposed to distance. You're fine using a d if you can't handle the x there. Okay, then our next one is x in this equation represents the x-axis. And when we're writing our equation, we have to put in there the variable that is plotted on the horizontal or the x-axis. In this case, that is time. And usually in physics, we use a lowercase t for time. Capital T is reserved for period. That's another way of measuring time that we'll talk about in the future. Okay, and let's look at M and B. M, hopefully you remember from math class, is the slope, and the slope is going to be the rise over the run. Okay, so how high up are we going compared to how far over are we going? That's also going to be change in the y-axis over change in the x-axis. You can think of it either way. Perfectly fine. And the last one, letter B here, represents the y-intercept. So our y-intercept is right over here. That is the value of whatever variable we have on the y-axis, in this case position, when the variable on the x-axis is equal to 0. So the way we'd interpret this for this particular Labor diagram is that when t on the x-axis equals 0, position on the y-axis equals 1. So if we're going to write an interpretation for the y-intercept, we would say that when time is 0, okay, when we started the stopwatch, the tumble buggy was already at a position of 1 meter or 1 meter from the origin. So now let's look at actually writing out this equation. So usually we're going to use graphical analysis with lab data because it is messy, and we're going to use the statistics in there to do our what's called linear regression. Since I gave you guys really nice data here for this example, let's just look at the line here. So we're going to go with, again, y equals mx plus b. So first thing, let's go ahead and substitute in our variables. So for the y-axis, again, we have position, which typically we're going to use x for since this is horizontal position. The x-axis has the variable time, so I'm going to put in a time there. Next, let's take a look at slope and y-intercept. Y-intercept's easier. I'm going to do that first. So I just come over here to wherever 0 is on the x-axis. I follow that up, and our line is at 1 meter on the y-axis, so I'm going to put in 1 meter. So on any of our constants where we have a number, not a letter, we always want to put the units. We know what we're talking about. Is this meters, centimeters, micrometers, inches, if you happen to be using the English system. The last one's a little trickier, and that's going to be the slope. So remember, the slope is equal to the rise over run, okay, or change in y over change in x. And on this graph, got a nice grid system here, so I can just say, well, for every 1 second I go over, I go up. 1 to 2 is 1 meter, 2 to 3 is a second meter, so that is 2 meters. So here I could say my rise is 2 meters, and then my run is 1 second. So for every 2 meters up I go, I had to go over by 1 second. So that's what we mean by doing rise over run. You could certainly come out over this way. Okay, so here we see from this point going all the way up to 7, from 1 meter to 7 meters, that would be 6 meters. Okay, so make sure that you look where you're starting, look where you're ending. Don't just count boxes on these, because sometimes I'll space them out so they're every 2 meters or every 10 meters, just whatever works. And in order to go up 7, from 1 to 7, so 6 meters, we have to go over 1, 2, 3 seconds. So 6 meters over 3 seconds. And hopefully you recognize this is going to be 2. So 2 divided by 1 is 2, 6 divided by 3 is 2. And then we want to keep those units, meters per second. So we're going to substitute this guy in as meters per second. Okay, so this is going to be our final equation for this particular tumble buggy. So the equation that describes this tumble buggy's motion is x equals 2 meters per second, t, plus 1 meter. So that tells us that the starting position of the buggy was 1 meter, and as we've talked about, that slope represents the velocity. Its velocity was 2 meters per second. Okay, come back in for the next video, and we'll talk about applying this equation and seeing how we can apply it in multiple different situations. As always, any questions, please send me an email or talk to me in person.